Okay, thanks everyone for being here. So this is a joint work with Aviv, and it's actually very similar in the settings to what Hao just talked. So maybe I will take this opportunity to extend on some more technical details and give our perspective. Okay, and Aviv really wanted you to see this poster. Our work is like called Two Barriers to Collusion, so it's like two lessons. Okay, so the basic setting is that we are trying to design the priority mechanism for the blockchains, how to decide which transactions are included in each block. So there is already a line of work that gives different definitions that we, like axiomatic definitions that we might be interested in. And for the purpose of this talk, we are mainly going to focus on the single item case, as if there is only one transaction, because I'm going to focus on characterizing what are those different axioms mean in terms of the actual mechanisms that implement them. Okay, so in some sense, this is just another auction, just for transaction prioritization. But there are several reasons to think that this is a bit different than the regular auction. Mainly that you do want to maybe add some more security, or you want it to become a bit more secure. So one thing is that you have miners that are more ephemeral. So it's not like the same auctioneer all the time, and it's not like a very repeated interaction, but maybe there are some miners that change all the time. Some of them might be anonymous. So you have less trust in the auctioneer that is running the auction. Another thing is that collusion is maybe made easier by side payments and smart contracts. One other difference is that you have burning, which is easy to implement in this case. So this gives you like an additional primitive that you might use in your design. So usually when we think about auctions, we have the allocation rule and payment rule. Here we will also have the burning rule. And yeah, there are some notions. So the mapping from what Hao talked about is like MIC is like MMIC and OCA and OCA and SP. So maybe the first thing is to understand the difference between OCA and SCP. And if we try to give a definition, maybe without formal notation, it would be that a mechanism is OCA proof if for any coalition of the miner and some bidders, they cannot exceed by some deviation, by some joint deviation, they cannot exceed the joint utility of the current or the intended implementation coalition of winners together with the miner. Okay, so this is our benchmark. In this case, if we have a single item auction like mechanism, and we have, and the bidder one is the one that is the highest bidder is bidder one, and that's the bidder that is supposed to win, then the intended joint utility would be the utility of miner and bidder one, and the alternative utility is the miner and bidder two. With SCP, you would consider this coalition against itself in the alternative world where they deviate together. Okay, so it's different benchmarks. And so I would say SCP is a more game theoretic notion in the sense that you have like notions like group strategy proof or something like that. So you're considering how the group acts together to benefit itself. And OCA is a bit different, and we will try to understand. So there is the posted price example. In this case, let's say there is a single transaction you can allocate, and someone, I mean the protocol or EIP 1559 or someone decided that the posted price needs to be 1.5. But it happens to be that in this instance of the transactions, no one is actually has a willingness to pay 1.5, and so what do? So you just don't allocate, but you can bypass it with a off-chain agreement. So the miner can agree with this bidder that the bidder would bid higher, so the protocol would approve the bidder, and then the miner would cash back the bidder, so everyone is happy. So indeed, the intuition is that OCA is maybe the users working together against the protocol, and SCP is the users working against each other, and it actually can be exploited by the miner to benefit itself. We will see this now with two examples. So two examples to show you cases where SCP and OCA are different. Okay, so one is the second price auction. What the miner can do in this case is cooperate with some losing bidder and ask the losing bidder to drive up the price. So instead of getting the second price auction, the second price as intended, the losing bidder drives up the price to be close to the first bid. And then the joint utility of this collision of the miner and the losing bidder becomes higher because the miner can earn more, and they can share at least some of this profit with the losing bidder. But this is a bit weird because, first of all, it doesn't change the allocation, it doesn't change maybe the welfare. So it's we would like to have a nicer example or a more surprising example. So let's take the third price auction, and I know it's not like a very commonly used auction, but we will just use it for the theoretical understanding. So in the third price auction, the highest bidder wins and pays the third highest price, not the second highest price. So let's look at the valuations on the left. So what's going to happen is the highest bidder with value 1 would win and pay 1/4. So the miner revenue is 1/4 and user 1's utility is 3/4. Now the miner can cooperate with the second highest bidder, ask the second highest bidder to bid much more than the first bidder. They win the item. Now bidder number 2 wins the item. The miner revenue stays the same because we pay the third price, and the third price didn't change. And the user number 2 now gets 1/4 because the true value is 1/2 and they pay 1/4. And in this case, the miner didn't strictly make any gain, but they can arrange in advance side transfers to make sure this is Pareto optimal. So the common thing about these two examples is that the miner kind of used the ability to form coalitions with different subsets of the users to drive up the price and their own utility. Okay, so we have we already have a bunch of negative results about SCP, and it was left open to see what happens with OCA. So the way we will do it is basically by first characterizing OCA, OCA with other axioms, and then eventually this will lead us to the impossibility of having everything at once. Okay, so the first thing maybe to see before we go into the characterization is that anyway we will have to have zero revenue. And this comes from looking at the single bidder case. So we found looking at the single bidder case to be very useful to drive many of the results. In the single bidder case, you have payment and you have burning. And if you examine the utility of the single bidder, it's going to be the value, if it is allocated, minus the payment. The joint utility of this bidder and the miner is the value, if it's allocated, minus the burn, because the burn disappears, but the payment goes to the miner. But then what this means is that in terms of the expression, the payment and the burn look the same if you just replace these two expressions. And we know from Merson's result that once you set up the allocation, it uniquely determines the payment. So in this case, it will also uniquely determine the burn if you require OCA. And that would just mean that the payment has to be the same as the burn and zero revenue in the single bidder case. But this can also be extended to the multi-bidder case using the miner incentive compatibility, because if the miner gets no revenue in the single bidder case, they could make up users and they do get some revenue in the multi-bidder case. They could just make up some users in order to simulate this situation, but we cannot allow this if we require this. Okay, so now let's try to understand how do deterministic. And an important thing is that this result also, the first result also holds in the single bidder result also holds in the randomized case, and this will be useful later. So how do deterministic OCA mechanisms look? And this is like an exact characterization. We're going to have a burning function that depends on the number of allocated bits. Okay, so if there is one transaction allocated, we burn this amount. If there are two transactions allocated, we burn some other amount. Then we are trying to maximize the welfare in some sense. So we are allocating transactions as long as their value is above the total burn. Okay, I mean, we try to maximize this expression of the value allocated minus the burn. And if we look at the difference function between the burn, so every time we allocate more transactions, we change the burn, right? So we have this burn difference function. And if we look at this burn difference function, we see that in most mechanisms that we know, this burn difference function is constant. Like in the Bitcoin TFM, it's 0 because we don't burn anything. In the T+ version of EIP 1559, it's constant. So it's like a linear function of the number of allocated bits. The interesting thing maybe is what happens if we vary this difference function. And the interesting design pattern that we noticed is that actually if you make this burn difference function strictly increasing, then maybe it's possible to extract more revenue in this way. The reason for this is like the critical bit characterization of DSIC. So let's say, I don't know if this graph is very self-explanatory, but the orange lines are the burn amounts. Okay, so if there is one transaction burned, we burn delta type of 1. If there are two transactions burned, we burn the sum of delta type of 1 and delta type of 2, and so on. Okay, and we keep allocating transaction as long as the burning difference doesn't go over the value of the allocated transaction. And now when we get to deciding payments, we need to decide the critical bid, and the critical bid is going to be the last delta that we approved. So what happens here is that everyone pays the high delta, but what is burned is like the sum of deltas, which is strictly less than that. So this could be like a way to drive revenue. But if we restrict it to the single item case, again, to have a better characterization, then this translates to any mechanism that has a constant burn, which also serves as the reserve. So you have to have higher valuation than this burn in order to enter the block. And also you have to, because of OCA, you have to allocate to the highest bidder. And you have some freedom to set the payments. Okay, so OCA doesn't really determine your payments, it determines the allocation and the burn. So what's left when you now add DSIC or MMIC is that it determines the payments for you. So if you add DSIC, it's going to look like second price auctions with reserve. If you add MMIC, it's going to look like some form of generalized first price auction. But this is, if you add all of this together, the payments are not going to work out, and you cannot have the mechanism. So this is like the result. But this is for deterministic mechanisms. And so I will shortly talk about the randomized case. So How showed an impossibility result for the randomized case. But there was like one extra assumption, which I guess is very reasonable, which is that we assume a finite confirmation rule, but we do not assume a finite inclusion rule. So inclusion rule is maybe you use some more space of the block to justify your allocation or to prove that you acted by the protocol. So we do not assume that it's finite, and this technically what it means is that you don't have to totally forget. I mean, okay, there is some technical difference, that's fine. And then you get maybe a bit weaker results that are still open to some possibility, but we don't know to show a mechanism. But we know how to restrict a little bit the space of what you can achieve with this type of randomized mechanisms. So first of all, you cannot have scale invariant mechanisms. This means that if your mechanism scales with the, the allocation of your mechanism doesn't change with the size of the bits. So if we multiply all the bits by 10 or by half, then you still have the same allocation. And some very natural mechanisms look like that, like the second price auction, third price auction. But not all mechanisms look like that, because, for example, if you have a second price with reserve, then you have this magic number like the reserve price that your allocation depends on. So we also want to have results for maybe scale variant mechanisms. And now we use some tension that we identify between the single bidder case and the two bidder case. So in the single bidder case, if you remember, we characterized that you have to have zero revenue. And in the deterministic case, we could have used MMAC to show zero revenue always. But in the randomized case, that's not exactly what you get. You get that the burn for two bidders must surpass the high bidder payment. And this is again to prevent the miner from creating shares, because otherwise they could use this kind of arbitrage. But then this brings you to the two bidder case, but then this result also propagates back into the single bidder case due to OCA, because OCA, if you find that you burn too much because of the two bidder setting, one of them might decide to give up on participating in order to increase the joint welfare and reduce the burn. So this kind of you kind of have this cycle that affects the single bidder case again. And using this tension, you can kind of bound the possible welfare that any mechanism might have. So just a last note on future directions. So we have this impossibility. It's still possible that with this infinite inclusion rule, you could have randomized mechanisms that work. So it's interesting to look for them. You could also rethink the collusion options, because I think there is good basis to think that they might be flawed to some extent. And also I think this design pattern that I showed you with the OCA characterization is quite interesting. So maybe we could think like of a non-constant burn difference EIP 1559 or something like that, if you like to increase revenue. Maybe you don't like that. Okay, so thank you everyone.